Swayam Prabha. Digital India. Educated India.
Hello, we were discussing a special feature of calculus of variations which is called general variation. Normally we have made functions to be unknown, but over a fixed domain x1 to x2 if it is one variable case. But now we are relaxing that. We let the domain of the function that we want to find is also variable, because that leads to an interesting set of problems that we discussed partly last time. We will discuss more today. So, looking at the problem, we have this concept of general variation, where we, as we can see here, so we are looking at a function y star which we think is a solution that minimizes a functional j which has an integrand f which depends on y and its derivatives. Then we say that our domain x1 to x2 is not given to us, that is variable. So, we let that have also variation as it is shown here. So, we have the domain itself from x1 to x2 is going to be undergoing the variation, just like y undergoes variation, which we have here delta y1 and delta y2. We also let the domain vary, and here we differentiate between the h that we are using and delta y that we have here. So, which is the relationship that we have derived in the last lecture. It is not really a big derivation, all we are doing is extending the curve from here to here, there to there, because x1 to x1 plus delta x1 does not exist, but x2 to x2 plus delta x2 exists. So, we need to interpolate this way, extrapolate this way and that way. That gives us basically looking at the slope here, that is why we have y1 double prime and then y1 double prime over here and then y2 double prime over here. That is how we got the delta y and delta y2. And what we did here, if you look back, is a very simple manipulation. When we have this integral to be done from x1 plus delta x1 to x2 plus delta x2, we divided it into x1 to x2 and then added and subtracted these portions that we needed to do, because this additional thing we need to do, that is nothing but f at that point, because delta x2 is so small, we get this term, and then we have to subtract, because we are not doing really from x1 to x2, x1 to x1 plus delta x1, that we are subtracting. Okay. With this we got the boundary condition now, which looks like this, right. This is what we had when our integrand was a function of y and y prime only. Then we said at the end of the last class that if we have a functional such as this here, this integrand, right, is a function of w and w double prime. It is actually not y, it is w double prime square, because that is what will be there in the beam, right. So, we are talking about a case where we have a beam that is allowed to slide on one end. This is what we were discussing last time. So, let me draw it here again. Let us say I have a beam, this is the beam, and if this is not fixed at the right end, but is allowed to move on a curve. Here I have shown it as a straight line, but now we can say it is a phi to x, that curve is given, it is on a slope like this. Now, if we apply force on this, if I apply some force on this beam, how does it deform is what we are asking. Again, there are a lot of possibilities, but now our integral is not 0 to L, because that L is not fixed, because when the beam bends, let us say like this, it is going from here to here, not the complete length. So, what should be the boundary condition for this now, because the domain is now variable, that is when we need this general variation. Okay. So, for that we do not have a condition like that yet, and that is what we will do now, because our integrand now has not just w and w prime. In this case, of course, w prime is missing, but a general case is that our integrand depends on y or w, w prime and w double prime. Okay. When you have that, we can do the same thing. We take a general one now, as if our integrand has y, y prime and y double prime. If we have it, again we do the same thing, in the sense that we do this changed functional from x1 to x2 and then add this part and subtract this part, because the new functional was supposed to go from x1 plus delta x1 to x2 plus delta x2, but we are doing from x1, we do not want from x1 to delta x1, that gives rise to this term, and then we are stopping at x2 here. So, we need to add the extra part over delta x2, which gives us this term, and again if you do the usual integration by parts and all that, we get the boundary condition, we get the differential equation part, where fundamental lemma will give us, actually there should be a delta or h should be there. Let me just erase that. So, this is, yeah, there should be an h here, and then we have h prime and all that. We apply fundamental lemma and make this thing equal to 0, that gives the differential equation. We get the usual boundary condition, and then we get this additional condition here, okay, and then this h, the usual two boundary condition that we get, and then f delta x. Now, when you have h, we said that h is different from delta y now, because h is at some point, again if you go back to this, at any point the distance between these two curves is actually h, as our usual perturbation in the function is, variation in the function. But what we call delta y is a corresponding point. See, x1 was here, it has moved to this point, x1 y1 was here, it has moved x2 y2 here. So, those two if we compare, that gives us delta y1. Okay. So, this is now delta y1. Okay. So, the same difference we have to make here, saying that h1 and delta y1 is related in this manner, which we had already used. Now, we just take a derivative of this. So, h1 prime becomes delta y1 prime minus y1 double prime times delta x1. Likewise, delta h2 prime will become delta y2 prime minus y2 double prime delta x2. So, we can substitute for this h prime here and h here at x1 x2, meaning h1 h2, h1 prime h2 prime. If you do that, we get the boundary conditions that look like this. Now, we had three boundary conditions. There is the first one that says f y double prime delta y prime x1 x2 equals 0, that is the usual one that we already had, and similarly we have this condition f y prime minus f y double prime prime times delta y, that is also known to us already. What we had, these two we already know, but this third one is the new one because of variation in the domain. Whenever domain is variable, we have to satisfy this, because delta x in that case is not 0. So, that must be 0, a long thing that we have here. Okay. That is the condition. Now, get back, and differential equation of course remains the same, that does not change. So, differential equation does not change. This is something important to remember, does not change when the domain is variable, when the domain is variable. Yeah. So, that is something that we must remember. Okay. Only the boundary condition, we have this extra boundary condition that involves y and y prime and y double prime in some sense. Okay. Now, this is basically capturing what we have. When we have an integrand that depends on y, y prime and y double prime, we would have the boundary condition, which this is expanded version. This is the extra boundary condition, extra BC. Now, if you see, this and what we have here are not the same, because at that point we still had y and y prime, but now we have let that point move along a function phi 1 x, phi 2 x. Earlier delta x was domain was variable delta x 1, delta x 2, but now the delta x 2 and delta y 2 are related because they have to lie on this line, delta x 1 y 1 related because they lie on that line. So, we have this relationship, delta y 1 delta x 1 are related, and hence when you take derivative, these two are also related. Here it is phi 1 prime, here it is phi 1 double prime, and then we have this relation and this relation. If we now substitute this delta x 1 or delta y 1 that we have in terms of the other, we get an equation that is this long one that we get by adding, and the new thing that appear here as this phi prime and phi double prime that come about, the boundary curves where the boundary has to go. Okay. This is more general version of the so called transversality conditions. Transversality because this is only when you have a particular form of the functional, which is f of y square root of 1 plus y prime square, f of x, not f of y, f of x square root of 1 plus y prime square. If you have functional, then these curves being normal like what is shown here, the orthogonality transversality holds. For all others, we still call them transversality conditions, even though they are just very general ones. Okay. Noting this, in this case phi 2 is given to us, we go back to this equation that we have and look at our functional. Okay. So, we look at our functional that depends on, again this is not y double prime, this is w double prime, this is w double prime, and when you substitute all the relevant things over here, okay, phi 2 that is given as a straight line, all that, we get this condition. Okay. This multiplied by delta x at x 2 because that is variable, but then delta x 2 is not 0 because it is variable. So, what multiplies this thing is equal to 0, that is what we have put, okay, because this is not equal to 0. Okay. What does it physically mean if you were to compute this half E I w double prime square minus q w minus E I w double prime prime phi 2 prime minus y prime plus this is actually not y prime again, this should be w prime E I w double prime w double phi 2 double prime minus w double prime. Okay. This is just a typo, right. Now, if you do that at x 2, right, that other end, that is L that you have, what it should mean? It means that when it is allowed to slide here, okay, there will not be any force there, there is no reaction force. Whatever reaction force that will be at this end will be in that direction. Okay. That is what it means physically. The tangential component of the reaction here along the curve is going to be 0 because it is free to move in that direction. Okay. Similarly, if we have two functions in one variable, then what happens? That is, we are minimizing a functional j with respect to two functions y of x, z of x simultaneously, where our integrand depends on x, y, z, y prime and z prime. Okay. Then we know the differential equations. Again, differential equations do not change, we are emphasizing that. It is only that we say the boundary conditions are different. We are saying that x1 and x2, the boundaries are controlled by two functions phi1 and phi2. Okay. There is a relationship between y and z at one end and other end. Two functions are there, they are connected to each other, right. In that case, we can establish transversality conditions that are shown here. Those of you who are interested can derive these in the same manner that we followed when we get the transversality conditions. We can do that. Note that now we have two functions y of x and z of x, and they happen to be satisfying a relationship at either end at x1 and x2, right. Using that, when we do it, we get transversal condition of this form, because again the domain will be variable in this case, x1 x2. When they have to satisfy, you are not able to freely move, because between y and z there is a relationship. You cannot have x whatever you want, and that is when you get these conditions. Okay. For many other problems also you can derive transversality conditions, because again let us recall the kind of generalizations that we have used in extending calculus of variations of one function in one derivative. We extend it to many derivatives and then several functions, and then we also extend it to from one independent variable x to y, x and y 2D, x, y, z 3D. For those also one can write transversality conditions, because they are very useful in many problems pertaining to engineering physics and in geometry as well. And there is this notion that we can now very quickly use to what we talk about smooth functions. So far whatever examples we have considered, the solutions have always been smooth, meaning they are differentiable. What that means is that we can take derivative of the functions, but what about points like this, right. So, we have this is a smooth function, this is a non-smooth function. If you look at this point, which I will put a big red dot there, that point is not smooth, right, not differentiable, because there is no unique gradient at the point. It is going there and then suddenly changing its direction abruptly, as opposed to a curve that smoothly goes like that, right. So, for such things, if a solution is of that kind, we will soon cite an example where that happens, a very simple problem, but that has a non-smooth solution. How do you do that? How do you deal with those? In fact, such extremal curves are called broken extremal. Broken in the sense not that a line is there and it is made into two pieces, not like broken like that. Normally if you take a wire and that wire bends like this, you say the wire is broken, right. It is not made into two pieces, but it is just that at that point it looks like somebody broke, right. It is broken. Okay. So, we can use this variable end conditions to talk about this broken extremals, okay, or non-smooth things. So, we look at that middle point in a interesting way. So, if I have a problem where I have to go from 0 to L, okay, I will draw the domain. If I have to go from 0 to L, and if I suspect that at some point in between there might be a broken point, meaning that a non-differentiable thing, let us call that xc, or original j, the functional, we can split into j1 and j2, that is from here to here j1 and from here to here we call j2. Then we write down our boundary conditions that we have discussed in the last class and today, that we write these conditions. Now, what we say is that whether you take x1 or x2, because what multiplies this delta x for either case for this xc, this is the end point for this domain, okay, that is the first domain. If I take y1 curve, this is beginning point is known, this is not known, and here beginning point is not known, end point is known, right. At this interface, that is xc, what we say is that this thing and this thing should be equal, and so it should be this one and that one. So, f y prime and f minus f y prime times y prime will be equal at that interface. The y prime, y1 prime, if I say curve on this one is y1 of x, on this other domain if this is y2 of x, we are not saying that y1 prime is equal to y2 prime at xc, because that is the broken extremal. So, we are not saying y1 prime evaluated at xc is not equal to y2 prime evaluated at xc. They are not equal because the thing is non differentiable, right, but these quantities are the same. They are the continuity conditions. Dou f by dou y prime evaluated for y1 at xc, for y2 at xc, they are the same, and also this f minus f y prime times y prime is continuous across the interface. So, you can see variable and condition how it comes about if you just split the domain into 1 and 2 and evaluate j as a summation of 2 functionals. Okay. So, if you do that, we get these conditions. They are known as Wierstrass-Erdmann corner conditions. Corner meaning again this is a corner, okay, like a non differentiable point, okay, a kink. Kink is a corner, they are called corner conditions. Okay. And what is continuous as a corner condition is what we just said, f y prime and f minus f y prime times y prime. Okay. Those are the continuous and they are known as Wierstrass-Erdmann corner conditions. Now, let us take an example that we had taken in the very beginning to talk about Fermat's conjecture about refraction of light. The light, he said, does not take the least distance path, it takes the least time path, and we had said like a funny problem, if there is a dog and there is a rubber duck in the water, the dog does not go like this because it cannot swim at the same speed as it can run on the swimming pool floor. So, what it would do is to take a path that is broken like this. Again, if you look at refraction, sort of a dog running on swimming pool floor and swimming in the swimming pool, we say light rays when they are in glass versus air, their speeds are different. So, it would go like this and bend over to the other point, right. So, this is our broken point or corner, this is our broken point or corner. So, we can apply this corner condition. So, here we have to minimize the time, the functional remains the same, differential equation remains the same, and hence the solution being a straight line here and here remains the same except this corner. How do you find this point? If I say this is x1 and this is x2, right, over here we have xc, the interface. At that point we have this condition, that is 0 to x0 to xc and then xc to L. So, we have two things here, this is in air and this is in glass. So, we are going from x1 to xc in air and then xc to x2 are equal to L, this is x1 is equal to 0, 0 to xc in air, okay, and then xc to L in glass. The speed is different. Now, we have to minimize this sum of two functionals. That is a variable end condition is this xc. There we know what is continuous, which is the corner condition, these two, right. So, here f is 1 plus y prime square by v, that is what we had in our thing over here, that is a f for our problem integrand that depends on y and y prime, and f y prime is given by this and f minus f y prime times y prime is given by this. These two should be the same. That is what we do, whether at the interface, whether the discontinuity of this one will actually give us the what we call the the Snell's law, because y prime we have V air and this we have put, and we also see from trigonometry that y prime is nothing but tan theta in the air, tan theta in the glass, right. If you do this, we get the relationship that sin phi air by V air. Again we have converted theta into phi because of the way normally in refraction when you state Snell's law, you measure the angle from the normal at the interface. So, if you have this is the interface, if the light ray comes like this and goes, right, we draw the normal and we measure the angle here. Whereas, when you say a curve, we measure the slope here. So, this is theta, this is phi, that is the relationship here. Theta is pi by 2 minus phi, that is why from theta that we had we converted to phi here, we get Snell's law. So, the very first problem in calculus of variations involves an advanced concept of general variation to arrive at it. Earlier we had done this problem using one variable normal, not calculus of variation, normal thing where we say xc is unknown, and we had done that. We assumed that these two are straight lines. Now, we have differential equation that tells you a straight line. We say variable and condition here, there is a corner, the light ray has a kink at the point where it is going from air to glass, and that can be solved using this Wierstrass-Erdmann corner conditions. So, what we discussed here is how to handle variable end conditions that dependent on this concept of general variation, where the domain itself is perturbed, and that led us to what are called transversality conditions, and later we said that in between there could be a broken point which is a kink or a non-differentiable point or a corner. So, we have Wierstrass-Erdmann corner conditions. We also quickly looked at a two function case. In fact, more such cases can be studied. That is just one thing that we have y1 y of x and z of x, and y and z could be related to each other by at either end. More such situations can be studied. Okay, we just considered one example as an appetizer. Okay. So, this is one important thing, calculus of variations, where the domain itself can be variable, and we can consider that as well. Okay. Moving on, we will return to mechanics a little bit more later, so that we can apply all that we have learnt to mechanics and design in the next few lectures. Thank you.